Okay guys, welcome back to Math 1800, which is pre-calculus. My name is Resh Mahaber, and we're here to talk about working with higher order polynomials. Now, we just got done talking about graphing higher order polynomials, right? So once again, we just need to figure out what the intercepts and what the roots are, and then from there, the intercepts and the sign chart is, and then from there we can graph it. Now, we talked about some stuff, and I'm going to put an example here that we left off with last time. See if I can paste this, if I remember how to do it. Okay, which is this guy. This is where we left off with our last function, right? So the interesting thing is, if I had to graph this, it's pretty simple. Why? Because I can find the intercepts. And actually, let's do it real quick. I'm just going to get the quick sketch to graph intercepts. Note that the y-intercept, plug in 0 for x, that's 16 times 1 is 16. The x-intercepts obviously is going to be 4, 0 and -1, 0. Now let's try to figure out what the sign chart is. The sign chart, and we talked about this, your x-intercepts are really your zeros. And because we have no denominator, we're really not going to have any bad guys. So this is going to be -1 and 4. These are both zeros. And note, the big key here behind graphing this is multiplicities, right? The multiplicity here is a 2. Why? Because there are duplicate roots here. There's a 2 here as well. So what does this mean? Well, this is all going to have the same freaking sign, it looks like, because even roots, even multiplicities, keep the same sign. They don't. What's the word here? Alternate. They stay the same. So, and because we know that when we plug in 0, we get a positive out. That means it's going to be positive and positive. So if I wanted to sketch the graph, it'll look something like this. Boom, boom. I'll have zeros and -1. And 4, right? Now here's something that's cool, because the multiplicity is 2 around the root. It better look quadratic. Boom, boom. Don't forget, we have 0, 16 is going to be our y-intercept. So now connect all the dots. It's going to jump through here, and it's going to go up forever and go up forever. So this is what it's kind of going to look like. Okay, very, very simple graph. But what was this all based off of? It was based off of the effect that we can solve this. If we can't solve that, game over. So what if I took this back a step? What if I took it back a step? What if I took it back a step? What if I said the exact same thing, but I said, hey, guys, I want you to solve, see, x squared minus 8x plus 16. What am I doing? I'm just multiplying it together. X squared plus 2x plus 1. And God, if we multiply this out, we get x to the 4th plus 3x cubed plus, what's 3 plus that? So this is going to give me -5. I'm going to need you to trust me a little bit on this one. This is going to be a -5x cubed plus 1 and 16, 17. And then so plus 1 more x squared plus x's is going to give me -8, blah, 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 32. Okay, so you guys get the point. I think this is going to be it. Probably not 100% accurate, but here's the point. If I multiply this out and got here, what if we started here and this is our original problem? Well, then we have a slight issue, don't we? Because how the heck do we even break through this to get it to look like this so we can make all this goodness happen? That's what we need to talk about. Okay, so let's expand this out and let's get to working. All right. Well, let's start slow before we move any faster. Okay. Well, there's some good stuff that we already should know about here, and this is kind of let's start. What I mean by let's start slow. When we solve any guy, because this is what this really comes down to is I'm setting this equal to 0. This function equal to 0 in order to get these x-intercepts. So literally, we're just solving this, right? So what if I were to say, I want you just to solve this. Solve, let p of x equal, for polynomial, right? X squared minus 5x minus 6. And I want you to find p of x equals 0. Okay? So this really means I'm just going to do this. X squared minus 5x minus 6 equals 0. Then you're going to factor this, right? And I'm breaking this from brass tacks from the beginning. Okay, and I want you to pay attention to some details. And normally we'll just go from here to the next step, which is x equals 6 and x equals negative 1. There's a step here that we skipped, though. That goes right here. Do you guys know what it is? It's setting each piece equal to 0. This is a big key here. Now notice, you see how we just subtract this over. So what's the moral of the story? If I know that x equal negative 1 is what we call a root or a solution, then x plus 1 is a factor. And a factor of what? It's a factor of the original polynomial. Okay, so that means, and I want you to think about this. If this is a factor, then that means it goes into this evenly. So knowing something's a factor is huge. So if I know something's a root, then I know it's a factor, and vice versa. So maybe I shouldn't say if then. Maybe I should say if I know I have this, then I know for sure I have this. So likewise, if x equals 6 is a root, then I know for sure, vice versa, I can conclude that x minus 6 is a factor. It's really, really clean. Like, it's not really, really hard detail, okay? So this is moral of the story. So if I have a factor, I have a root, and I have a root, I have a factor. This actually has a special name. It's actually called the factor theorem. Okay? And what does the factor theorem say? It says exactly what we just said, that if this thing is a solution, if x equals a is a number, is a solution or root, then see how we kind of just subtract it over and get x minus 6, right? Then we know that x minus a is a factor. Okay? And of whatever polynomial we're working with, of whatever the polynomial is. Okay? Very, very brass tacks. Let's do an example real quick. Okay? And I'm actually going to work forwards to backwards. Now, here's the idea. This is we're solving, right? So potentially, we can put this back together again. Like Humpty Dumpty puts them back together again. So check this out. Okay? What if I said this? And by the way, this might be a slightly longer video. I'll probably put it in 2 segments so you guys get everything you need. Okay, what if I said this? Given 3 and negative 2 are roots, okay, of a polynomial p of x. Okay, this is what I want you to do. I want you to construct a polynomial. Well, the polynomial p of x. Okay? So what's the idea here? If I know these two are roots, so I know x equals 3 is a root, that means what? That means that x minus 3 is a factor. Boom. And likewise, if I know x equals negative 2 is a root, then once again, add it over, I get x plus 2 is a factor. It's really, really simple, is it not? So the idea is just this. I want you to work backwards. And I want you to think about how our solutions were put together. Here when we solved, we factored each piece, we broke it apart, and then we solved each one. Well, let's do the exact same thing, but backwards here. X equals equals 3, and x equals negative 2. Go back a step. That would be this. Plus 2 equals 0, right? If you have a root, you have a factor. And that's what we just did right here. Well, guess what? We're making the polynomial. That means that x minus 3, if you multiply this guy and this guy together, right, we get this, which leaves us to x squared minus x plus 6. So equals 0. So this is my function that I was trying to find, the p of x function. So p of x, one function that can do this is x squared minus x plus 6. Now, obviously, there can be constants, and this is kind of the big thing. If you have an a in front of here, like a constant, it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if that's the case, whatever that constant is, we can figure it out by them giving me some additional information. So what we're going to do is we're going to be constructing the polynomials. We're working backwards as opposed to solving for them, which is actually kind of cool. Okay, so here's another polynomial. So I could give the exact same answer. except for, let's say I threw a 5 in front. It wouldn't change anything, right? Because 5 equal to 0 doesn't change anything. But it's still the exact same polynomial. Okay? That's just simple. Now, what's the whole point of factor theorem? And we'll do more examples of this. So let's say I actually said something like, I'm going to give this thing, right, that looks like this. I want you to solve x cubed plus 2x squared minus x minus 2 equals 0. Now, some of you, if you're really good, you guys know some extra skills, like factoring by grouping. Ooh, fancy, fancy. Well, the good news is, if they do this and I say, given that x equals 1 is a root, okay, so I want you to solve this given that this is a root. Now, what do you know? Well, let's look at this. If, and we'll put this in a different color because it's the green line. If x equals 1 is a root, then what do we conclude? X minus 1 is a factor. Of what? Of x cubed plus 2x squared minus x minus 2. Okay, so here's my point. I want you guys to list the factors of 24. And I'm going to erase this, so I'm just going to throw it somewhere. 24, what are the factors? 2, 3, 4, 6, 8, 12, and then 24 and 1, right? Why are these called factors? Because they all divide into this guy evenly. Divide into them evenly. Now, some of you probably say, I don't need division in order to do this because I know my multiplication tables. Well, guess what? You don't know any x cubed plus 2x squared minus x minus 2 multiplication tables or your x minus 1 multiplication tables. So how do you do this? Well, good news. Once again, if you're a factor, right, of this, so if you're a factor, that means you go in evenly. That's the big piece of the puzzle here. So what does this mean? That means if x minus 3 goes into this guy, then that means I can long divide x minus 1 into x cubed plus 2x squared minus x minus 2. And there should be no remainder. Everything should go in perfectly evenly. Alright, so you're probably saying to yourself, well, Resh, I haven't long divided in a whole semester, and I'm totally confused. So let me remind you, in order to long divide, what you look at are the highest degrees of each polynomial that you're dividing. In this case, it's x and x cubed. And then you ask yourself, go to the side, and you say to yourself, how many times does this thing go into that thing? So this thing is x, go into that thing. It don't say 3 because that's not the answer. It goes in exactly x squared times. Alright, so that means x squared goes here. And then you're going to take this and multiply it through by the entire guy here. So that gives you x cubed minus x squared. Alright, so far so good. Now, depending on the instructor you had, he would put a parentheses here, or she would put a parentheses here and put a little negative here. That tends to be more confusing to me. So what I said to do is, because we're subtracting this entire quantity, I'm distributing my negative into everything. You'll see that this cancels, and what does it leave you with? 3x squared, and then bring down everything else. Now, what's the point here? If it's a factor, like we listed over here, then it should go in evenly. If it goes in evenly, we should be able to do this, and then we should have no remainder left. So here we go. How many times does x go into 3x squared? Remember, highest degree here into highest degree of the remaining thing that we're dividing. Well, that is 3x times. So we get 3x squared minus 3x. Now, here we go. Let's change colors again. Got to distribute a negative in. Boom, boom. Drops. Then this is going to give me 2x minus 2. Finally, how many times does x go into 2x? Just 2 whole times. And this is a very, long division is a very important key, guys. Like, if you're not good with long division, I really don't know what you're going to do when you guys get the calculus. So please be good with long division, and it's a very important key. distribute a negative in, it drops. Look, no remainder. So what is the moral of the story? The moral of the story is if we have a root, we have a factor. If we have a factor, it goes in evenly. If it goes in evenly, we can long divide it in. If we long divide it in, then finally we know that x cubed plus 2x squared minus x minus 2 equals 0. So we know that this thing breaks apart into x minus 1 times something else. What's the something else? X squared plus 3x plus 2. Congratulations. Now we can finally solve this guy. And good news, if we couldn't factor this, what could we use? Quadratic formula if it was necessary. But it's not necessary here because x minus 1 factors into x plus 2 times another x plus 1 equals 0. Notice that now we end up getting x equals 1, x equals negative 2, and x equals negative 1, which are all of my solutions that I need to solve. As you can see from our first problem, which was graphing, if we needed to do that guy and actually figure it out, we would have to go through this entire process just to factor it out because these solutions would end up becoming our x-intercepts that we would need to graph and to put on our sign chart. So note, these are tools. This is a tool that you're going to have to put in your toolbox and actually be good with doing. So what did we learn today? That we can long divide in a factor into something else to break it apart. Very important key. What else did we learn? We learned that if we have a root, we have a factor. If we have a factor, we have a root, right? And if we have a root, we have a solution. Those are all synonymous with one another. Okay. What else did we learn? That you can long divide in once you have a factor, and it should go in 100% evenly. Okay. Now, notice the factors here were even factors. Now, we have a slight problem. What if we have a factor like this? So here we go. I'm going to give you one more example. And this is what I want you guys to do. Okay? I want you to solve this guy. Solve. And this is solve x cubed plus x plus 10. And I'm going to give you something. I'm going to give you that x equals negative 2 is a root. All right. So do you see how this factors? And I'm always going to say that try to see if you can factor this. This should always be the ante to play. Try to factor it. If you can, great. If you can't, then so what? We just got a lot of work we got to do. So if we have a root, what's the factor? X plus 2 is the factor. And what does that mean? X plus 2 goes into this evenly, so it'll be x plus 2 times something equals 0. How do I figure out the something? Well, here we go. Let's long divide. X plus 2 goes into x cubed plus x plus 10. And now let's get to working. X goes into x cubed, x squared times. So this is x cubed plus 2x squared. Distribute your negative in. Notice this drops. Now, guys, let's slow down for a second. Some of you guys put 0x squares here. I can't tell you how garbage that is because you don't put 0 x's on anything. A coefficient with the x with a 0 doesn't even make sense, okay? Pay attention. These are x squares, these are x's, these are 10s. None of it adds together. So you're just going to bring it all down. And if you say to yourself, well, can I put the zeros in there? Yes. It will come back to bite you in the rear end eventually, though. So I would refrain from doing it, and time to grow, time to evolve. So x goes into this guy how many times? Well, x goes into 2x squared, that's negative, and negative 2x times. This gives me negative 2x's. And then finally, I can multiply it in. It gives me negative 2x squares minus 4x. And then distribute our negative in, which I will do in red, which I did not do previously, so I will clean up my previous guy. Here we go. That's in red. That's in red. Distribute my negatives, which makes these positive. He goes away. And then finally, what are we left with? We're left with 5x plus 10. Now note, because it's a factor, what should it go in? It should go in evenly. That's the big key here. So x goes into 5x 5 whole times. You get 5x plus 10. Negative, negative, boom, boom, 0. And if this doesn't happen, you screwed up somewhere. That's what it comes down to. So what does this mean? This means that now we have that x, something happened. Oops, sorry guys. Now we know that x plus 2, and the thing that goes in our fancy little question mark area is going to be x squared minus 2x plus 5. Congratulations, we have officially figured out what the other factor is. Now we could finish solving this because that's our job, to solve. So we end up getting this. Now, question, we know x plus 2 is going to equal 0. We get x squared minus 2x plus 5 equals 0. How are we going to solve this? Congratulations, guys. This is called quadratic formula. Yes, yes, yes. Don't forget, it's still one of your tools, and it's still the ante to play. So x equals negative b, which gives me a positive 2, plus or minus the square root of b squared minus 4ac all over 2a. This is 2 plus or minus the square root of negative, was that 16? Over 2. And this gives me, okay guys, recall, square root of negative anything is going to have some I stuff going on here. This is 4I. So this is 1 plus or minus, whoa, I got ahead of myself, divided by 2, which is 1 plus or minus 2I. If you factor out all the goodies. Now, the question is what did I just do here? Well, that means your solution, so all in all, your solutions is negative 2, 1 plus 2I, and 1 minus 2I. Alright guys, this is where I have to rant and rave. You see this? Now, fractions and whole numbers, they come by themselves. See? But imaginary numbers come in some particular form, and we call this form conjugates. This should be familiar based off our video that we had on section 2.1 where we were rationalizing, evaluating the functions. If you don't get it, I would tell you to go look at section 2.1 and look through the details. But conjugates, meaning that, once again, if a minus b shows up, his conjugate is a plus b and vice versa. So what does that mean? You cannot have one without the other. If you get 1 plus 2i, for free, you get 1 minus 2i. Now, that's a beautiful thing. That's a beautiful thing. All right, so let's show you how this applies in our next example. Okay, next example. So once again, now this is another thing. This is a lot of stuff going on. You get conjugates along with all of this. So if I give you another factor and there's a conjugate, that means you can multiply some stuff in and get to working. Okay, so here we go. Here's the nitty-gritty. All right, so suppose I give you this. Suppose, all right, let me get this. Okay, guys, sorry about that. I had a slight glitch in my computer. So suppose we had a another function, and let's say I gave you this. So this conjugate thing doesn't just happen with imaginary roots, okay, or what we call complex roots. We get them when they happen with irrationals as well. So here we go. Long story short, we're about to have some goodies coming to a theater near you. So let's try this guy. Suppose we know that x equals 1 plus 2i and x equal 1 are roots. I want you to construct a polynomial where these are the only roots, okay? And what the heck? Also make it so the lead coefficient and the lead coefficient is 2. All right, guys, so here we go. I know one root is 1 plus 2i. I know another root then, because I get it for free, conjugates is 1 minus 2i. Also, I know x equals negative 1 is a root. Now, notice they didn't tell me a degree, so it would have been nice if they would have said, actually, let's do that. Our roots, construct a degree 3 polynomial. Now, by them telling me degree 3, that lets me know that all I can have is 1, 2, 3 roots. Now, if they said degree 4, that would imply that I needed a multiplicity on this root, right? Which we'll do in the next example, or we'll just alter this one. A degree 3 polynomial. So what do I do? And we'll talk about this coefficient at the end. Maybe I'll leave this out until the next example. Okay, what do I do? Well, if this is a root, imagine yourself subtracting these over. Remember, we're going to construct these. So x minus 1 minus 2i, x minus 1 plus 2i, and x minus 1 are all the things that need to be in here. Now, I can't just multiply this and this together. Guys, these are conjugates, and they're conjugates for a reason. They're actually going to multiply, and the i's will end up going away. So I'm going to encourage you not to look at this as a trinomial. Look at this as these two are together, x minus 1's together. And remember, because the conjugates are supposed to generate the difference of squares. And this are together. So notice, why did I highlight them in different colors? A minus b times a plus b. So this should give us a squared minus b squared times x minus 1. All right, so this gives me x minus 1 squared. Anybody remember what this is? I squared is going to give me negative 1. So this is going to make it plus 4 times x minus 1, which is going to give me x squared plus 2x, oh, minus 2x. Sorry, guys. Forgetting how to do multiplication. The video is running a little longer than I wanted, but I think you guys are getting the point, which is good. So technically, right now, this is a degree 3 polynomial that I'm constructing. So that's x cubed minus x squared minus 2x squared plus 2x, and then and by the way, I do this to kind of help me group my terms together. X cubed minus 3x squared plus 7x minus 5. Here's my degree 3 polynomial. Boom. That has all three of these as roots. And good news is that all three of these are contained inside here. Now, let's say and I'm going to take it from right here. Right here. Okay. So technically, I could have stopped right here. I didn't have to multiply it out. And I'm going to tell you that in class because it's really not worth my time to do it. If they said that the lead polynomial had a degree of 4, now remember, these come in pairs. So if I square it, that means I have to have a multiplicity on one of these 3 roots because it's only those 3 roots. That means either I'm going to square one of these 3. Well, guess what? If I square this guy, he comes with another pair, so I have to square him too. That makes it degree 5. That's no good. That means I'm only left to square the x minus 1, put a multiplicity or a duplicate on that guy, which would change my polynomial altogether. Okay, so if you multiplied it out, this would be totally different. But once again, whatever they ask for is what you're going to construct. Okay? So what did you learn today? Factor theorem is huge. That's more or less the moral of the story. If you have a factor, you can long divide it in. You know that imaginary roots come with conjugates. Okay? And once you know this stuff, then we can now solve all the degree 2 or degree 3 guys. Alright guys, I know the video ran a little bit longer. The next video we'll talk about what do we do when we don't have that root. When we don't have that x minus 3 goes into it, or x minus 4 goes into it, then what do we do? Well, if the root is rational, we could do something called the rational root theorem. Okay guys, so I'll catch you guys on the flip side. But in the meantime, remember, keep pushing. These problems are not about intelligence per se. It's about stamina because these problems are extremely long, especially when you follow the train of thought. Okay, here's one problem to try out. Solve this guy. F of x equals x cubed plus x squared minus 10x minus 12. And I'm going to give you, what am I going to give you? I'm going to give you, given that x plus 3 is a factor. Alright guys, solve this. Solve f of x equals 0. And I'll collect it from you in the morning. So with all that being said, I know the video ran a little bit longer, but it was good. It's good. A good solid part. It's actually a longer section in the book. So once again, send me an email if you have any questions. Once again, this is Rush Mahaber. Signing off.